Here we have a frequency distribution for shoe sizes. This is in the 170320 document. This is number 2. So we take the shoe size information and we set it up as a frequency distribution, and then we calculate the mean, we calculate the deviations, the squared deviations, we take the frequencies of our squared deviations and get the total of all our squared deviations, which will be this, the total of our deviations squared. Find the mean of the deviation squared, the total deviation squared divided by the sum of the frequencies being the same as n, and that comes out 66 over 73, which is very close to 0.9. So our standard deviation is the square root of the mean deviation squared, and that's of course the sum of the square root of the sum of our x minus x bar squared, because x minus x bar is a deviation and this is a square, divided by n, the number. That's going to be our mean deviation squared. And we take the square root of that. Square root of 0.9 is very close to 0.95. So we have our mean deviation squared, and now we sketch our normal distribution. It corresponds to the assumption that this is a normally distributed, the shoe sizes are normally distributed. And I did mention that Napoleon, I'm not sure whether the whether Napoleon's need for what turned out to be the normal distribution preceded development of the normal distribution or not. But Napoleon needed to know how many shoes of different sizes to make for his army, and everybody said, okay, so let's assume it's a normal distribution. And went from there, and it seems to have worked out quite well. So you can kind of look up the history of that. It's kind of interesting. Okay, so here we have, again, a normal distribution with the mean in the middle. The mean turned out to be 10.03, and I just rounded that off to 10. And the standard deviation, 0.95. And of course, I did some rounding here, and it really doesn't make much difference because the 0.03 is really pretty insignificant. So I labeled the mean plus the standard deviation, 10 plus the standard deviation, 10.95, and so forth. 10 minus 0.95 gives us the 9.05, and we see where these numbers come from. Then we, again, construct our histogram. Now, I didn't go through the details of how I located these points, but we construct a histogram for this data, and it looks something like this. And it's reasonably similar to the histogram that you get, we constructed a histogram based on the normal curve that we got from our data, and we see that that histogram does a pretty good job of matching the histogram we get if we use the actual data, meaning that this distribution really is pretty close to normal, and that the shoe sizes, as we would sort of expect, appear to be normally distributed. Now there's one thing we go on to do, and we're not going to do that this class, so we're going to do this next week. So I'll mention it now that these, the mean is at what we call z equals 0. One standard deviation to the right of the mean, well, z equals 1. Z just stands for how many standard deviations you are from the mean. Okay, go another standard deviation, z is 2. Go a standard deviation less than the mean, z is negative 1. 2 standard deviations less, z is negative 2. So these numbers, 8.1, 9.05, 10, 10.95, 11.9, correspond to z values, negative 2, negative 1, 0, 1, and 2. We'll do much more with z values, but that would be a good thing to kind of lock into your understanding before next week.